All right, now we're gonna go ahead and solve quadratics by hand. Solving quadratics by hand and looking at the imaginary space as well. Imaginary, okay? So for example, we're gonna look at mostly perfect squares, or easy radicals to solve by hand. Say you have x squared plus 16 equals 0. I'm going to graph this for you so you can see. If you have x squared plus 16 equals 0, again, don't put the equals 0 part. You'll get a graph that looks like this. Okay, so you can sketch it, and you would say that there are, you can sketch it here, y-axis, x-axis. There are no real zeros, none. This curve does not touch the x-axis, so there's no solutions. Visually, it doesn't touch this x-axis at all, right? We call it no real solutions. I'm going to show it to you another way. Say you have x squared minus 16 equals 0. Let's graph this one. X squared minus 16 equals 0. Interesting. This one graphs perfectly where there are zeros. It touches the x-axis at -4 and 4. Those are the solutions. We've solved it. So if you see an x squared plus 16 equals 0, or an x squared plus 4, x squared plus 1, any of these kind, they're all going to have no solutions, and we'll see why. No real ones. The minus ones do. Okay, so let me show it to you by hand on why, and this will bring us into the imaginary space as well. So if you have x squared plus 16 equals 0, we could also solve this quadratic, not just graphically, but algebraically. So what are the x-intercepts? Meaning we're solving for x. What x value, what number squared, add 16, would equal 0? What number squared, if you add 16, would equal 0? That's what this is asking. So we can graph it, and it's telling us, the graph is saying there are no x values. It's impossible. There are none, no options. Okay, so what does this mean? Well, we would subtract 16 on both sides. X squared equals -16. Because we want to solve for x. We want to solve for x. We're looking for this unknown number, x. So subtract the 16 on the other side. So what number squared will equal a -16? It's the same thing. Well, what number times what number? Remember, x squared means a number times itself, the same number. So twins, doubles, right? What number times what number will give you a -16? Let's try 4. What's 4 times 4? Is that -16? No. Okay, let's try -4 times a -4. Is that -16? No, because a negative times a negative is always a positive. Okay, what about -4 times 4? Oh, did we get it? Oh yeah, that does equal -16. Oh, no, these are not doubles. These are different numbers. So, oh, never mind. Not doubles. So it's impossible. There are no numbers, none, no numbers that if you multiply it to itself will give you a negative number. So write that down. There is no number in the universe. There's no number times itself, right? That will equal a negative number. It is impossible. Impossible. So I want you to watch this video, Imaginary Numbers Are Real, real quick.
Let's say we're given the function f of x.
And we're gonna see why visually there are no solutions, no real ones. Why does this not touch the x-axis? And why is it that if you were to try to solve for this x value, that we're figuring out there is no x values. It's impossible. Okay, so I want you to look at it visually here.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary.
All right.
To get a better handle on imaginary,
So, there are no real solutions if you were to graph x squared plus 16, but there are solutions. They're imaginary solutions, so we're going to go ahead and do it by hand. That's the only way really to find out these solutions. So we just said that x squared equals -16. We want to solve for x, right? So we're trying to figure out what is the square root of -16, right? What does the square root mean? Well, make sure you watch square roots or radicals in a different video. But square roots are the square root of 4, or radical 4 is plus or minus 2. Square root of 9 is plus or minus 3. The square root of 1 is plus or minus 1. 16 is 4. Square root of 25 is 5. Make sure you know your square roots. Go ahead and list all of them. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25, right? So make sure you know that it's plus or minus, because a -1 times a -1 is also 1. A -2 times a -2 is also 4. -3. So make sure you know your doubles. 1, 2, 3, 4, 5, 6. Go all the way down to 15 and make sure you can pause the video and list your doubles there, your perfect squares, okay? So we can take the square root of 16. What number squared equals -16? Or what's the square root of -16? Same thing. Well, it is impossible, like I said, to take the square root of a negative number, because there's no number that when you times it to itself, right, multiply it to itself, that would give you a negative number. It's impossible. So what we can do instead is, the first thing, we call the square root of a negative 1, I. Write that down, square that, huge in your notebook. The square root of a negative 1, we call that I. It's just what we call it. It's imaginary, impossible, right? Lateral, whatever. We can call it L if you want. Different dimension. So you can take the square root of negative number if you take the negative out, right? So let's take the negative out, the negative 1 out, the imaginary part out of it. Let's rewrite the radical negative 16 as radical negative 1 times radical 16. It's the same thing. Negative 1 times 16 is negative 16. We're just rewriting it separately. So now we can actually take the square root of 16, which is plus or minus 4. Because 4 times 4 equals 16, and also negative 4 times a negative 4 equals 16, right? So plus or minus 4, and then your I, and just rewrite it. The real comes first, and then the I. So there are no solutions visually. It doesn't cross the x-axis, but there are. X squared minus 16 has solutions, which is negative 4 and 4, aka plus or minus 4. You can do it also algebraically. Add 16. This is the one that has actual solutions. X squared equals 16. So you're adding the 16 over here to get rid of that negative 16. What number squared equals 16? Well, negative 4 or 4, right? Either one. So plus or minus 4. That's why visually you see negative 4 and 4 when you graphed this. And algebraically, you also found that 4 squared minus 16 is 0, right? 4 squared minus 16 is 0. 16 minus 16 is 0, right? And negative 4 squared minus 16 equals 0. Negative 4 times negative 4 is 16, minus 16 is 0. This has two solutions, this equation. This equation has two solutions too. They're just imaginary. So it's the same thing, it's just adding an I at the end. Like, this is impossible, so like fake world, like, yeah, the solutions are negative 4 and 4, kinda, psych your mind, right? But it's not imaginary, it's just lateral. Your solutions are on a different dimension, as we saw here. They're not on the x-axis. Here, it's pulled out more, right? So this is the one, it's on the lateral space, right? A different plane. So we'll do a couple more of these. All right, so you have x squared plus 25 equals 0. Well, if you were to graph it, you would see that x squared plus 25 equals 0. It's way up here at 25. It does not cross the x-axis at all because it's impossible, right? So let's find the solutions, the imaginary ones instead. So subtract your 25, we'll do it by hand, right? To get x squared by itself, so we can solve for x. Take the square root of both sides, so x equals the square root of negative 25. What number squared gives you negative 25? Impossible, right? So you can do it by taking the imaginary out, take your I out, right? Gouge your I out, and then keep the real in, right? Now we can do it. What's the square root of 25? 5 plus or minus 5. Bring your I down, bring your times down. Remember, the real comes first, then the fake, right? Imaginary. Again, not fake, just playing around, right? Plus or minus 5i is what x equals, okay? So that's how you do those. I'll give you one more because it can get a little more, not tricky, but a little bit weird. X squared, 2x squared plus 48 equals 0. Okay, we're adding more numbers, right? if you were to graph it, 2x squared plus 48. There it is. It's at 48. It's just a skinnier parabola because of the 2 in front. It doesn't cross the x-axis. It's imaginary. So let's find our imaginary solutions. Subtract 48. 2x squared equals negative 48. We want to get x squared by itself. So divide by 2, divide by 2. X squared equals negative 24, right? Let's take the square root. What number times itself will give you 24? None. 4 times 4 is 16. 5 times 5 is 25. It would be a decimal point, right? We don't want decimals for this. We want to simplify or break this radical down. So, again, let's first take the imaginary out and keep the real. 24 is not a perfect square, okay? So instead, we're gonna find perfect squares. So let's make a factor tree. What number times what number gives you 24? Again, use these numbers. 4, 9, 16, 25, 36. Which one of these numbers will give you 24? Let's use this one. 4 times something, right? Radical 24 is the same thing as radical 4 times radical 6. It's the same thing. But we're looking for perfect squares. There's one. So take it out. Radical 4 is 2, plus or minus 2, right? The square root of 4 is 2. Make sure you break this down to double check that you can't break it down anymore. You can't, because 3 and 2 are not perfect squares. You're done, right? So just leave that 6 inside. Bring your eye down right there. Okay, so the square root of radical negative 24, or excuse me, the square root of negative 24 is plus or minus 2i radical 6, because we found a perfect square, which is radical 4, which is 2. Radical 4 equals 2, because 2 squared is 4, right? 2 times 2 is 4. Okay, so that's how you do that. Let's try another one. Let's see if 3x squared plus, let's see. Let's try 1 second here. 3 times, no. Let's try, okay. All right, let's try 3x squared plus 144 equals 0. If you were to graph it, it would have no solutions. Again, same thing. It would not touch the x-axis. So let's find the solutions, the imaginary ones. Well, subtract 144 from both sides. So we can get the 3x squared by itself. We want to get this x squared by itself, so divide by 3. X squared equals negative 144 divided by 3. Do your math or use a calculator. 3 goes into 14, 4, 12, 2 left over, 8. Negative 48. You cannot take the square root of a negative number. It is impossible. So take the imaginary out. And let's go ahead and break down the 48, okay? 7 times 7 is 49. These are perfect squares. This is not. 48 is not a perfect square. So we got to break it down and find perfect squares. So I need some room. Let's find a perfect square. Well, 16 times 3 will be 48. That's perfect. Okay? I think, yeah, 16 times 3, 18. Yeah, double check your math. 16 times 3 is 48. Look at that. We found a perfect square. So the square root of 16 is 4 plus or negative 4, right? Keep the 3 in and bring your I down. Don't forget it. So your roots are x equals positive 4i radical 3 or negative 4i radical 3. Yeah, so that's how you do that. I could show you another way as well. If you were trying to radicalize 48, like do a factor tree, if you don't know 16, that's fine. You could do 8 times 4, right? And just keep going. So the way you do it, you just keep going forever till you can't go anymore. And you circle your pairs. There's a pair, bring it out as one number. There's a pair, bring it out as one number. Not a pair. Let's see, 8 times 4. Oh, that's wrong. 8 times 4 is not 48. Wait, 48. 6 times 8. So you can just do, okay, say you don't know that 16 times 3 is 48. Just do numbers that you know, right? 6 times 8 is 48. And just keep going. 3 times 2, right? 4 times 2. 2 times 2. Okay. Then you circle your pairs. So bring that out, that pair out as 1. Bring this pair out as 1. Keep the non-pair inside. 2 times 2 is 4. Keep that 3 inside, right? And then put that I right here. The real comes first, then the I, then your radical. But you could do it that way. I'm not going to go over factoring. You need to watch factorization. Go on YouTube and type in factorization on how to factor numbers, all right? How to do that. 8 times 10, 5 times 2, 4 times 2. Like, you got to watch another video on that. That's a whole separate video. But that's how you solve quadratics when there's imaginary involved. If you notice that there are no real solutions, right? No x-intercepts, then just subtract your number, and then factor tree the 25 out, right? The radical, the square root of 25 is 5. This is imaginary, so put I. You gotta put your plus or minus. If it's not a perfect square, like 48, you gotta find your perfect square. So 16 times 3. The square root of 16 is 4, and then leave the non-perfect square inside the radical. If you're having trouble with how to factor out numbers like this, comment below or come ask me. But yeah, that is solving quadratics. In the imaginary space, right? The lateral, different dimension. But there you go. Good luck on doing your imaginary. And I think that's about it. Make sure you know this right here. Okay, that was it.